Okay, hi everybody. Welcome back to section 4.6. And in this section, we're going to take a look at another example of a non-homogeneous differential equation that we would need to use variation of parameters for. So let's look at this differential equation, y double prime minus 9y equals 9x over e to the 3x. So this 9x over e to the 3x right here is not a finite product or sum. Okay, so that means we need to use variation of parameters. Okay, so we need to use variation of parameters because of this 9x over e to the 3x. Okay, so we need to solve this non-homogeneous differential equation. Just always remember some key components is that this y double prime minus 9y is the homogeneous component of our differential equation. That's where we obtain our complementary solution. And this 9x over e to the 3x is our non-homogeneous differential equation component, and that gives us our particular solution. Okay, so we want to solve this. When we solve one of these, we always take our first step, and that is solving the complementary solution with the auxiliary equation. So let's go ahead and start our solution. So we'll say solution, and we'll say step one, and that is solve the auxiliary equation, or excuse me, solve the complementary solution solve the complementary solution y sub c using the auxiliary equation. And that's from section 4.3. Okay, so that's the first step. And so the homogeneous component that allows us to solve this characteristic equation is the y double prime minus 9y equals 0. Okay, because remember the standard form for a constant coefficient homogeneous differential equation is that ay double prime plus by prime plus cy equals 0. Okay, so here a equals 1, b equals negative 9, excuse me, b equals 0, and c equals negative 9. So when I set up my characteristic equation, that would be 4m squared plus or minus 9 equals 0. Or excuse me, no 4. That's what I was a bit distracted by. It's just n squared minus 9. So this actually works out pretty cleanly. Okay, so this is just m squared equals 9. M equals, be careful here. Uh, Square root of 9 is just plus or minus 3. Okay, so we have actually distinct roots. We have m equals 3 and negative 3. Okay, so we have distinct roots. Okay, remember that the solution for distinct roots is y equals c1 e to the m1x plus c2 e to the m2x. So when I write up my solution, this would be y sub c equals c1 e to the 3x plus c2 e to the negative 3x. Okay, and here we're dealing with variation of parameters, so we know we're going to need a y1 and a y2. So just remember that this e to the 3x is my y1, e to the negative 3x is my y2. So we'll just make a note like note y1 equals e to the 3x, y2 equals e to the negative 3x. Let me clean these up. Okay, so we got the easy part out the way. Now what we need to do is get into our particular solution phase using variation of parameters. So we'll say step 2, get the differential equation into standard form, which means get y double prime naked. Okay, so my differential equation is y double prime minus 9y equals 9x over e to the 3x. Well, my y double prime is already naked. So here we'll say y double prime is already naked. So the differential equation is already in standard form. Okay, great. So it's already in standard form. You could say like check. And so since it's already in standard form, what we would say here is that this 9x over e to the 3x is our f of x, the input function. Okay, so already in standard form, that means we already have our f of x. So now all we need to do is set up our guess for our particular solution. But the one great thing about variation of parameters is that we always know what our guess would be. So, here we could say make a guess for the particular solution. And so, well, the guess would always just be u1, y1 plus u2, y2. And that's our guess. And here we'll say always our guess. Okay, so let's get into getting u1 and y1 now. So here we go. Step 4. This is get u1 and u2. So u1, the formula for u1 is negative the integral of y2 times our input function f of x all over the Wronskian of y1 and y2, and we're calculating this integral. So the first thing we have to do is get the Wronskian. That's the missing component we don't have yet. So let's go ahead and figure out the Wronskian. So first, we need to compute the Wronskian. All right, so Wronskian of y1 and y2, that would be the determinant of what are my y1 and y2? E to the 3x, e to the negative 3x. So this would be e to the 3x, e to the negative 3x. Derivative, careful with the chain rule. Okay, and now it's the determinant. We are cross multiplying, subtracting, so we get negative. Well, let's do it like this. We'll do e to the 3x times negative 3 e to the negative 3x minus e to the negative 3x times 3 e to the 3x. Okay, so when we multiply these exponentials, the e to the x is 3x minus 3x is just 0. So what we end up with is just like negative 3 um, e to the 0 minus 3 also e to the 0. So that's like just negative 3 minus negative 3, and that's just negative 6. So the Wronskian just equals negative 6. Okay, so we got the Wronskian. Let's jump back to our U1 formula. So now we could complete all our components. So U1 equals negative the integral of y2, which was e to the negative 3x. So e to the negative 3x times our input function f of x, that is 9x over e to the 3x. This is all divided by negative 6. Okay, so let's take out the constant. So this would be just 1/6 on the outside. Well, I guess we could take out the 9 too. So let's take out the negative 1/6 and the 9. So this would be 9 over 6 times the integral of x, and e to negative 3x divided by e to the 3x. Well, this just turns into e to the negative 6x dx. Okay, so with these variation of parameters, there's always one of these integrals, meaning either U1 or U2, where one is very easy and one takes a little more work. I believe we are in the more difficult one because this is going to require integration by parts. Okay, we're going to need integration by parts. Luckily, I think it's just going to be one round because u would be x, dv would be e to the negative 6x dx, du would just be dx, and v would be negative 1/6 e to the negative 6x for our integration by parts. And so remember, for integration by parts, it's uv minus the integral of v du. And I like to think about it as crossing over. So uv, v du. So this ends up being minus 6 reduces to 3/2, but negative 1/6 x e to the negative 6x minus the integral of negative 1/6 e to the negative 6x dx. Well, maybe I jumped to a step a bit. Maybe I could backtrack. Um, negative 1/6 times just x, uv minus integral v du. So let's clean some of this up like I did previously, but maybe I was just skipping us a couple of steps. So negative 1/6 x e to negative 6x This is plus 1/6 integral e to the negative 6x dx. All right, so we just need to integrate e to the negative 6x. We did that a couple times already. So this is going to be 3/2 times negative 1/6 x e to the negative 6x minus 1 over 36, because that would be 1 over 6. 1 over 6 times negative 1 over 6 is negative 1 over 36 e to the negative 6x. And then we distribute in the 3/2. And this ends up being negative 1/4 x e to the negative 6x minus 1 over 24 e to the negative 6x. And so u1 equals this. Or let's just bring it down here. U1 equals this, instead of having to rewrite it. Okay, so that was, I'm betting, the hard integral to work with. Not necessarily hard, just a little more work with integration by parts and having to use the chain rule and some mental U substitution. So let's check out U2 and see what that would give us. So U2 is the integral of y1 times our input function f, Wronskian of y1 and y2 dx. So y1 is e to the 3x. Okay, so let's input what we know. So this would be e to the 3x times our input function 9x over e to the 3x all over our Wronskian negative 6. And once you look at that, this is just canceling out. And so what I'm left with, let me take out those constants, negative 9 over 6. It's just x dx. Well, it's just the integral of x. So that's quite simple. So negative 3/2 times x squared over 2. So that is negative 3/4 x squared. And so that's what U2 is. So a lot easier than the previous integral. Okay, so that is our U1 and U2. So let's clean a couple things up. Let's say step 5. Step 5 is plug in all of our solutions, y1, y2, u1, u2 into our particular solution. So remember, our particular solution always is u1, y1 plus u2, y2. So our particular solution is negative 1/4 in that expression. So let's just write it down. 1/4 x e to the negative 6x minus 1 over 24 e to the negative 6x. That's my y. That's my u1. My y1 is e to the 3x plus negative 3 over 4 x squared times e to the negative 3x. So that's my particular. All right, so now we have my particular. Let's wrap this up for our general solution. So step 6, form general solution. Okay, and so the general solution is y equals a complementary plus the particular. So my general solution would be C1 e to the 3x plus C2 e to the negative 3x plus, I'm going to write it like this. I'm going to bring the e to the 3x up front. E to the 3x times negative 1/4 x e to the negative 6x minus 1 over 24 e to the negative 6x plus, or I guess I could take the parentheses off. Uh, I could say minus 3/4 x squared e to the negative 3x. And that's my general solution. Okay, so another long problem. These take a while. So just take your time, make sure you're integrating correctly. Uh, the complementary is always the easiest part. So take care of that business first. Make sure you're in standard form. Make sure you're integrating correctly. Make sure you're getting the Wronski in correctly and getting U1 and U2 done correctly. Okay. But that's it for this video. Thank you for watching this example, and I'll see you in the next one. Okay, take care.